Okay, we're going to be talking about differentiability today, and differentiability is kind of analogous to continuity, and the tests for it are going to look kind of the same. And for differentiability, what you have to have first is you have to have continuity. So unless you have continuity, so that's like a prerequisite for differentiability. And here, and by the way, your test, that one question on the test that said a function has a limit if and only if, and what was the answer? The left-hand limit equals the right-hand limit. And I think everybody who answered it right, except for one, somebody did a verbal explanation of it. It said mathematical, but I gave credit for that. But what you're going to see is in this, if for differentiability, it'll look the same, but instead of f of x, it'll be f prime of x. So the left-hand derivatives are defined and equal at x equals c. And then it also says it is possible for a function to be continuous at x equals c and not differentiable. And when you have these things here, a cusp, a corner, or a vertical tangent line, then even a continuous function is not differentiable. And yesterday in class, we had, for those of you who were here, we had a situation where in one of the exercises we did, there was actually a corner, remember? And the corner was not differentiable because we couldn't find the slope at that point. So that's what this is talking about right here. So let's go ahead to look at some examples of this. Okay, for one, we have the graph at the right has a vertical tangent and horizontal tangent, and says, ask the question, for what values of x in this interval is f not differentiable? So for what values of x is the function not differentiable? Based on what we had in that note card.
Show me 2.
So you think there are two places?
Oh, I'm saying at 2.
At 2, yes. So we'll say 2. Anywhere else?
Show me 0.
0?
I'll give Kylie credit for that.
Is that right?
She said it.
Yeah. And so what disqualifies x equals 0 and x equals 2? Okay, not continuous here, okay? What disqualifies 2?
It's a vertical tangent.
Vertical tangent. Okay, vertical tangent. All right. Next, prove whether g is differentiable or not. And here you have a piecewise function. And here I'm going to set this up for you according to, because you hadn't seen this. First you test for continuity. And you say, does f exist here? Yes. And you know that the left-hand limit, since f does exist, so g, excuse me, since g does exist, you know that if g exists, it's all going to be settled if the left-hand limit equals the right-hand limit. So all you have to do is set it up. You see that condition 1 is met because of this equal thing below. So we say the limit as x approaches 0 from the left of g of x equals limit as x approaches 0. What am I going to put here? From the right of g of x And so we just test here. And so we plug in 0, and if we plug in 0 on the left side, what do we get here? Plug in 0, what do we get?
1.
1. And then we plug in 0 here, what do we get? 4. Does 1 equal 4?
No.
So limit as x approaches 0 of g of x does not exist, right? So therefore, g of x is not continuous, therefore not differentiable. Now we're going to have examples where we meet this condition and then go on and show that, demonstrate. Do you have any questions on that? Hannah, you have any questions? You're okay? Gavin, you're okay on this? All right. Okay, we have this one right here. Let f be a function such that the limit as h approaches 0, so forth, equals 5. Which of the following must be true? Which of the following must be true here? We have f is continuous at x equals 2, f is differentiable at x equals 2, and the derivative of f is continuous at x equals 2. This one here, is f continuous at x equals 2? What do you think?
What was the question?
Okay, is f continuous at x equals 2?
I'm going to go with yes.
Okay. Okay, yes, why is that?
No clue.
Because
Okay, Aaron said he didn't know. Anybody else? Okay, it goes back to right here. Goes back to right here. Okay, it explains. Because here we explained why things, what you have to have be, you have to have continuity to have differentiability, right? And do you have differentiability here?
Looks like it.
Why do you have differentiability? Because if you didn't have differentiability, what would this be here? This would not exist. This would not exist if you didn't have differentiability. This is telling you that you have to have differentiability, because if you didn't have it, this thing would not exist. Okay? So because you have differentiability, you have what?
Continuity.
Continuity. And do you have differentiability? Yes, because you have a number there. If you didn't have a number, then that wouldn't be. But do we know 3 for sure?
no.
No, we really don't. We don't really know. I mean, it's possible, but we don't have enough information to verify that this thing must be true. So therefore, we have 1 and 2 are true.
So for there to be like, for the equation to equal a number, there has to be differentiability.
Yeah, there is, because remember that this limit is f prime of x. F prime of x equals the definition of derivative, which equals 5. Well, f prime of 2, excuse me.
Oh.
Right? So this is back to the definition of derivative right here
Yeah.
in the notation. So so f prime of 2 equals that, or equals first this, which goes to that,
Okay, I get it now.
okay? So very much a logic,
I get why you answered that.
conceptual problem.
I understand.
And in these types of problems, I find the best way to go over these is go over one condition at a time. See if that meets the, and then you have a compilation for everything that's true. Okay. Now this one here, just take a few minutes and try to do this one for a few minutes, and I'll show you this one. This one's kind of cool when you work this one out. Set up the continuity first, and then you can set up the differentiability on the right. But just try working on this a little bit. I'll come back to help you with it. So I worked out the first for continuity, and this is what I got for my equation. Does that sound right?
That's right.
That's what you got? Did you know where to
I think I
go?
did it backwards,
No.
but
Did you know where to go after this?
No.
Yeah. Well, that's why I wanted to see if you could get at least this far. So is everybody okay with this part of it? But we can't solve based on this alone because two unknowns, right? One equation. So what we do is we come over here.
yeah, I worked
And-
it backwards.
You did this first?
Yeah,
Okay.
I found P first, or I found K first.
Where the limit as x approaches 1 from the left side, not of f of x, but what? F prime of x equals limit as x approaches 1 from the right side of f prime of x. So now we go ahead and take the derivative, so we'll say the derivative is going to be 2 minus 2x, right? Derivative of that. And what's the derivative of the right side?
X, or
2x.
plus K.
Plus k, because the derivative of p is 0, so plus k. And so now,
Started there.
if we plug in 1, we're going to get 2 minus 2 times 1 equals 2 plus k, right? And then that's going to be 0. So I got k is equal to negative 2, is that right?
That's what I got.
And then if you have k equals negative 2, 0 equals p is equal to 2.
Okay, see, I found K
So,
first and then.
you know what's crazy? I was just looking at them like set up next to each other without like working it out, and I guessed that those were the right answers.
Oh, did you?
Yes, just in my head that made the most sense.
Oh, really?
Without
Okay.
working it out. But I didn't think it was right, so I just stopped. So I just went to the 0 equals.
No, you just, what it is, you just might have a really good intuitive sense for equations and numbers. That's the best explanation I have.
Like
'cause-
that, just looking at them like set up to equal each other, in my head I was like, well, how can they equal each other? And I can
Oh, okay,
negative
yeah.
2 and positive 2.
All right,
And,
yeah.
I don't know, man, I'm psychic.
I don't know, because there's some, it could be, but I think more, there's some level of understanding you have that you don't consciously recognize
I
maybe.
guess not, but, oh well. It's
But
gonna
for
be
me,
right.
I don't have, to me, I would have to work it out. I wouldn't have any such intuition at that level anyway.
If it's gonna be the right answer, I'm not gonna question it.
So you ever heard of things, sometimes it's better to be lucky than good?
That's what my mom used to tell me.
Yeah. No, but really that's a talent in mathematics. Some people really have intuition for things like that.
Nice.
All right, so what we have is if you go to this next exercise set, it's just kind of you just look and you see if the functions are continuous, differentiable, or neither, or both at the point. Continuous, differentiable, neither, or both. And here would be at x equals 3, 1, 0, 0, 2, 0, 2, and negative 1. So what do you get for A? Neither. For B, what do you get? Neither.
So for it to be differentiable, it has to have continuity?
Yes,
Okay.
yes.
Just making that
It doesn't have, now, it has a limit, right? This does have a limit, but not continuous, therefore not different. What about this one here?
Both.
I'm thinking this is both.
Yeah.
I mean, from what we see, and what you're looking for in differentiability, you're looking for the smooth curve, right? Either a line or something smooth. This one here, D is what?
Doesn't look like a smooth curve to me.
Doesn't look smooth, but it is continuous. Continuous, this one here, neither. This one here, continuous. This one here?
Continuous? Or is that?
Yeah, it depends. This could actually be, it depends on whether or not this is a corner. Do you think that's a corner, or do you think that's a smooth thing? Because you can have a line that at this point just changes into a curve. So that's sort of ambiguous. If we assume that's a smooth curve, which it may or may not be, we can just say both. Both, we'll say both question mark, won't we? Let's call it that. And this one here is
Continuous.
continuous, and why not differentiable?
That's a vertical.
Gives the vertical tangent. And I don't know about these other ones down here. I guess this would be at -3, of course, would not be continuous at -3. So I guess we can kind of ignore those things. And let's see what else we have here. Okay, it says find if f is continuous and or differentiable at the value of the function where the rule changes. So you're going to look for 2 here, right, at x equals 2, and work this out for continuity and differentiability. I want to tell you one thing. I had a student years ago, I forget her name, but she thought she was really slick, and she was. I'll give her that. But what she found out was, well, I'm just going to go ahead, instead of testing for continuity first, I'm going to go over here and test for differentiability. And then she said if f prime equals it on both sides, well then I know the thing's going to be continuous. But what happened?
What happened?
Yeah, I'll tell you what happened is she ran into an equation like this where the slopes were the same from left to right, and so it looked like this, but then when you looked for continuity over here, these things didn't match up. So it's possible for the slopes to be the same. It's possible for f prime, okay, limit as x approaches c of f prime of x from the left side equal limit as x approaches c from the right side of f prime of x, but for the other one not to be true. So that's possible. So that's why you have to go through the continuity first. So go ahead and do that, and we will